I'm start sharing the web camera.
Okay, good. So,
well, I think
since there is 18 person, it's just 2 o'clock now. I don't know, you want to, so that we can wait a few minutes, or we can start as you want?
We can wait more 2 or 3 minutes.
Okay. So maybe for everybody already connected, it seems that today we have about 15 to 18 person. The use of the tool is quite very simple. I will shut down your microphone so that if you are speaking during the talk of Joaquim Barros, there won't be any interference because we are going to listen each other in the same time. If you want to ask questions, you may raise your hand. You are on the bottom right, you have a small tool so that you can raise your hand. It means that we are able to see that you want to ask a question, and then I will open your microphone. Or if you want, you can ask your question here in the public area. Or you can also do it with the option part in private. If you want to discuss in private with colleagues or with the teacher, it's possible to do it right here. What we are going to do is maybe keep a few minutes at the end for discussion, depending on the time we have. So maybe during your talk you can just write your questions so that we are prepared to answer to it at the end. And I would like to thank Joaquim Barros, professor in University of Minho, Portugal, for this third webinar of the year. This will essentially focus on the shear strengthening of reinforced concrete beams with FRP material. External bonding material. And then, this session is recorded and is available with replay. At the end, I may send you a link, and the link will be also available on the website of the IIFC. And so feel free to send this to your colleague if you found some part interesting, because all of this is for free. It's just for teaching, essentially, without any purpose of earning money with it. So feel free to send the link to anybody you want. So Joaquim, are you ready to start?
Yes, thank you very much for the kind introduction. So good afternoon for everybody. Well, in Portugal here, it is 3 minutes past 13. And well, the talk of today, as Emmanuel has indicated, is about shear strengthening of reinforced concrete beams. In fact, this talk is quite close to the one that I did last year. Well, because it resumes what I think is the fundamental of this type of subject. And so the presentation is organized in these main 4 topics. So the first one is the fundamental concept of shear. The second is about materials and systems, but I do not spend too many time in this topic because in previous webinars my colleagues have already talked about materials and systems used for the structural rehabilitation of concrete structures mainly. And the third one is in fact the most relevant topic, or is the main part of this presentation, because it's dedicated to the EBR, NSM, and the ETS techniques for the shear strengthening. And finally, I hope to have time to talk a little bit about the Dabazon, that is a database that we are developing in the University of Minho, with the main purpose of assessing or verifying the reliability of the available design guidelines for shear. Well, going directly to the first topic, that is dedicated to the fundamental concept of shear. Well, in fact, when we have a reinforced concrete beam that fails in shear, it is mobilized mainly three types of mechanisms. This one is proportional, I designate with VCZ, is proportional to the concrete strength class. So what happens is this part corresponds to the uncracked zone of the concrete. The other one is VI, that simulates the aggregate interlock effect. And finally, the third one corresponds to the simulation or the contribution of the Dalloway effect, or the contribution of the longitudinal bars for the shear strengthening. Well, when we have the stirrups that are represented here, the stirrups, well, in fact, the stirrups has beneficial effects in all the previous terms, because, for instance, in case of the favorable effect for the VCZ, what happens is that when we have these stirrups, we have a larger uncracked concrete zone, and consequently, we have a higher contribution of concrete, of uncracked concrete for the shear strength. But the stirrups has also a beneficial effect for the VI contribution, for the aggregate interlock effect. Why? Because the stirrups crossing the diagonal cracks limits the crack width and the crack sliding, and the benefit, we have a direct benefits in terms of aggregate interlock, because the aggregate interlock is more effectively activated. And finally, when since stirrups is embracing the longitudinal reinforcement, so what happens is that it increases the shear stiffness of this flexural reinforcement, and so it is promoting or is increasing the Dowell effect. So in fact, the stirrups have this type of benefits in all the three terms that I explained before. Well, now, if we analyze also the contribution of the stirrups in terms of the profile of the shear cracks, it is quite clear that when we have a relatively or we have a high percentage or a good percentage of shear reinforcement, and when we have a relatively small flexural reinforcement, so the crack opening profile of the shear cracks has this type of increasing or linear increasing width from the top, from the uncracked zones up to the bottom surface of the cross section. So we realize that we have an increase of the crack width, while when we have the longitudinal reinforcement that is distributed along the depth of the cross section, like we have in these cases, so what happens is that we have an increase of the crack width up to a certain, up to the middle zone of the cross section, and then this crack width is almost constant. Well, in general, when we are assessing the FRP contribution for shear, we try to promote the occurrence of shear failure. And how we, in general, assure this type of mechanism is introducing a relatively high percentage of longitudinal reinforcement. And in this case, what happened in terms of profile of the crack width evolution of the shear crack? We realized that we have an increasing of the crack width, a pronounced increase of the crack width up to the almost in the center of the cross section, and then to like a spring effect due to the very high axial stiffness of the longitudinal reinforcement, so the crack width start decreasing as we see here. So this means that depending on the distribution of the reinforcement, the shear reinforcement, and also the flexural reinforcement, so the evolution of the crack width of the shear cracks is different, and consequently this affects the contribution of the FRP systems, because, well, in this case, for instance, the higher crack width is in the central part, so the FRP are much more activated in the central zone. Well, so in conclusion, the shear capacity of a reinforced concrete element depends on the concrete strength class. So when the concrete strength class increases, we have a higher shear capacity. Also in terms of the scale of the structural elements, the harsh effect, because, well, when, for instance, the ratio between the A divided by D and A, as I have previously indicated, A is the shear ratio. Look, A is the distance between the support and the applied load. And the A divided by D, D is the internal arm, is the distance from the longitudinal reinforcement up to the top surface of the cross section. And when A divided by D, the ratio A divided by D is lower than 2.5, what can happen is that the load part of the load can be conducted directly to the support. And in fact, in this case, we have a much higher load carrying capacity, but this is caused by this harsh effect. Well, the shear capacity, as we have already observed, is also dependent on the flexural reinforcement ratio, okay, due to the dowel effect. And also, it also changes the profile of the crack opening evolution of the shear crack. And it also depends on the axial compressive force, because when we have an axial compressive force, so what happens? We have it contributes to have a larger area of concrete, of uncracked concrete, and we have also a smaller crack width, which promotes or which enhances the aggregate interlock effect. Okay. So I hope that my voice is clear, and well, up to now you are understanding these concepts. Okay. Give me some seconds to take some water.
We are listening.
Emmanuel, are you listening well or not? It's okay?
Yes. Everything is correct. There's no problem.
Okay, good. Thank you. So now if the idea is now to present the fundamental concepts for that are supporting the analytical formulations that we will use to estimate the contribution of the FRP. But we need to start understanding, well, the fundamentals of the analytical formulation. So when we have the beam that is supported by a certain descending load, label of descending load. So in fact, what we have is the isostatic compressive forces. And then what happened? We have the compressive struts, okay? And we have the tensile ties, and these tensile ties needs to be supported, the tensile force needs to be supported by the stirrups. This is what we are doing. We are introducing the stirrups in order to support these tensile forces. Well, if we have a representation of the force that are formed when a beam is subjected to shear forces, we have, well, a compressive force in top part of the beam, the tension that is supported by the longitudinal bars, and we have a diagonal compressive strut, and we have a diagonal tensile tie. Well, from equilibrium, so the shear force that we designate by V is the vertical projection, okay? The shear force is supported by the tensile force in the stirrup that is now projected to the vertical direction, okay? So this is the force installed in the stirrup, and this is the inclination of the stirrup, and when projected to the vertical, it should be in equilibrium with vertical force. Well, but the force supported by the vertical or by the stirrup, and if, for instance, if the stirrup has two legs as is normal, so in fact we need to take into account that here we have 2 times the cross-section area of the vertical elements. Well, and the force supported is the number of stirrups that we have along this length, okay? So that is the inclination of the compressive strut. As I already told, this is inclination of the stirrup. And so this distance from this point to this point is Z. Z is in general 90% of the internal arm. And so Z multiplied by the cotangent of theta plus cotangent of alpha gives us this distance. And now, if the distance between these stirrups is S, so the number of stirrups will be N. Now, if I replace N here, and finally if I replace here, I can obtain what is the, I can obtain a relationship between the resisting or the shear force and the force supported by the stirrups and divided by the distance between the stirrups, okay? So this is a normal equation that we use to evaluate the number of stirrups to support the shear force installed in a certain cross-section of the beam. And finally, we need to verify if we do not have crushing in the concrete compressive strut. Otherwise, we have we can have a very brittle failure mode. Well, now, if we want to increase the shear capacity of a reinforced concrete beam by adopting or by installing FRP systems, well, we can have a contribution that is designated by BF, okay? So the total resisting force is the contribution of the concrete plus the contribution of the existing steel stirrups, and now adding a term that is the contribution of the FRP. Well, the contribution of this FRP, so look, in this case, I'm representing this contribution like having a hook configuration, okay, configuration, and I'm assuming that the thickness of the FRP is designated by TF, and we can have this FRP distributed continuously along the lateral faces and bottom faces in case of using a hook configuration. Or we can use only some strips of CFRP with a certain distance, and the distance I'm designating here, the distance is SF bar, okay, is horizontal distance between the strips of FRP. So FRP, but in general, for the shear strength of reinforced concrete beams, in fact, we are using, in general, carbon fiber reinforced polymers, or CFRP. Well, now, the contribution of the CFRP is the cross-section, is the product of the cross-section of the FRP multiplied by the effective tensile stress, and in fact, the difficulty of this evaluation is how to determine the effective tensile stress in the FRP and then project it to the vertical. So sin the beta. Beta is the inclination of the FRP. If we have, if the FRP systems, shear strength systems, if the distance between these systems is SF bar, so this means that in this distance, okay, we can have N shear strength system composed by FRP. And if I replace this here and finally in BF equation, I can obtain the contribution of the FRP for the shear strengthening. That depends on the effective tensile stress in the FRP, the thickness of this system, and the width in case of using strips. This is the width of the strip. DF is the distance from the top part of the CFRP up to the label of the flexural reinforcement. Look, TF is here, okay. And if I'm using the concept of a shear reinforcement ratio assured by the FRP, in case of a discrete reinforcement that is assured by strips of FRP with a spacing of SF bar. So this is the equation to obtain the FRP shear reinforcement. But in case of continuous reinforcement, so the equation is provided by this way. Well, and finally, I can, if I'm introducing the concept of shear reinforcement in this equation, I obtain this one. Well, it is very well known from the experimental research that, well, the effective strain, because, well, to obtain the effective stress, okay, in the FRP reinforcement, this effective stress is the product of the elastic model modules of the FRP multiplied by the effective strain. So now the problem is that how to evaluate the effective strain. And according to the available experimental research in this topic, we realized that the effective strain decreased significantly. Look what happened. Decreased significantly with the stiffness, of the FRP shear strengthening configurations. And this stiffness is a product of the shear reinforcement ratio by the elastic models of the FRP materials that we are using. Well, and this data was obtained by Professor Triantafilo some years ago, and this data is obtained by Khalifa, but we, in fact, Khalifa co-authors. But in fact, what happened is we realized that, in fact, we see a clear tendency for a decrease of the effective tensile strain with increase of the stiffness of these FRP systems. And it was proposed this equation that evaluates the R parameter, and then R is multiplied by the ultimate strain, and then we can have an estimation of the effective strain. Well, now I have a short presentation about materials and systems used for the shear strengthening, but I do not spend too many time in this topic because, as I told already, you have in the previous webinars, my colleagues talk about this. So this is the relationship between the stress and strain for several types of materials. But in case of shear strengthening, in fact, we are using mainly carbon fibers. So using wet layup systems or laminates. We use in general epoxy resins to bond the CFRP systems to the concrete substrate. And the properties is indicated in these tables. Well, I will not spend time on this because you know quite well this. In terms of FRP systems, we have the prefabricated that we can use bars, laminates, and then we are using an adhesive system to glue or to fix the FRP bars or laminates to the concrete substrate. Or we can also use a wet layup system that is formed by a sheet or a tissue, and it is also fixed or bonded to the concrete substrate by an epoxy system. To characterize these materials, we executed some compounds of laminates or wet layup systems, and we execute tensile tests in order to obtain the stress-strain relationship that, as you know, presents a linear elastic diagram and then fails abruptly. So this is the case, the type of compounds that we produce to characterize the tensile behavior of the wet layup systems. And it is also important to characterize the properties of the adhesives, mainly when we want to model the nonlinear behavior of reinforced concrete beams, reinforced strengthening with CFRP systems. In this case, it's important to know also what is the relationship between the stress and strain, and we realize that it is almost linear in the first stage, but then to the formation of micro cracks in the microstructure of the adhesive, we have a non-linear behavior up to failure. Well, in terms of strengthening techniques, we have, as I will analyze in this lesson, Well, I'm focalizing mainly in three techniques: the EBR, the NSEM, and the ETS. In the EBR technique, well, I will present the shear strength configurations must used in this technique. Well, also the shear strength effectiveness based on experimental evidence. And finally, I will present the design formulations according to FIB, European approach, the American approach, ACI, the Italian design guideline, and the Australian design guideline. And then I use an example in order to teach you how to use this formulation for how to use this formulation to estimate the contribution of the FRP system for the shear strength of a reinforced concrete beam. Well, this is some photos and schematic representations of the EBR shear strengthening solutions. So this is a U configuration. In this case, we are also using an anchorage system. In this case, we are using strips of wet layup systems to increase the shear strengthening of this beam. This is a special hell laminate that recently are being used also to increase the shear capacity of the beams. This is a special configuration of the EBR systems where it is executed some holes in the slab that is supported on the beam, and so in these holes it is make the anchorage of these shear strengthening systems. And the most common EBR strengthening configuration are those that is represented here. So this is a full wrapping, but I use the symbol O to indicate that it is a full wrapping shear strengthening configuration. We have also a HU configuration where the FRP systems are bounded lateral surfaces, but also in the bottom surface of the cross section. We have also the S that is sided. The FRP are installed only in the lateral surfaces of the cross section, and well, sometimes we use anchorage devices to try to avoid the premature detachment of the extremities of this U and side configuration. So I use plus, a sinus plus, to designate that we are using in this case some anchorage devices. Well, in terms of disposition or arrangements of the FRP systems, we can use discrete, that is these two cases, in vertical direction or inclined, and we can also have a continuous where we are using only one wet layup system or layer or more than one layer, for instance, inclined and horizontal, or even inclined or in vertical. Well, some colleagues have also analyzed the influence of installing horizontal or the sheets with horizontal orientation of the fibers. Well, I'm presenting here now some experimental results in order to show important aspects in terms of the effectiveness of the different shear strengthening configurations. For instance, in this case, this was a study carried out by Professor Khalifa, where we have the reference beam, CVT1, the CVT2. We have one layer of U configuration, and where the fibers are vertical. The fibers are in the vertical direction. The CB3, in the CB3, it was installed 2 layers. Okay, so we have a vertical layer, with the fibers oriented in the vertical, 90 degrees, so in the vertical. But we have also another layer in the horizontal, so it's a 0 degrees, okay? 2 layers in this case. In the CVT4 and in CVT5, we are using, in case of CVT4, we are using strips of wet layup system, so where each strip has a width of 50 millimeter, and the distance between the strips is 125 millimeter. While in this case, the same strips, or with same width, the strips with same width and same spacing are installed, but installed only on the lateral faces, okay? In this case, in CVT4, we are using U configuration, while in CVT5, we are using L configuration. And finally, in CVT6, we are using a vertical layer, a U configuration with fibers in the vertical direction, but we are installing in the top part of the U configuration, we are installing anchorage mechanism, anchorage device. Well, we have here the relationship between the applied load and the mid-span deflection. And, well, the first aspect, and is quite clear, is that when we compare the force deflection relationship obtained in the reference, we don't have any type of shear strengthening shear strengthening system, okay? So this is the maximum load. Well, and for the other cases, for the other type of beams, we realized that we obtain a significant increase in terms of ultimate load. So the increase is between 35% and 145%. A very, very important aspect is comparing here between the beam, where we have the 2 layers, 2 layers in U configuration, and where one of the layer have the fibers at horizontal direction, 0 degrees, and when we compare the answer of this beam, that is here, the response of this beam, and the response of the same beam, but where we only applied 1 layer in vertical, so we don't, in this case we are not applying an horizontal layer, we realize that the values are almost same. So the layer at horizontal direction has a very small contribution for the shear capacity of the beam. Another aspect is when we compare the beam that has vertical strips of wet layup system that is formed by strips of 50 millimeters width and space at 125. And when we compare this shear strength configuration to the one that is composed by the same type of strips, but placed laterally or on lateral surfaces, we realize that the hook configuration, is much more is much more effective in terms of shear strengthening than the one where we applied lateral phase, the FRP systems in lateral phases. So this is a very important aspect. And finally, we realize that when we introduce anchorage mechanisms, we increase significantly, and look, in this case, it was possible to transform shear failure mode in a flexural failure mode. Okay. Well, now this is the typical failure mode. So we have the bond in case of a continuous system formed by wet layup system. And well, we have here in this case, we have also the rupture of the FRP and the bond. Okay. Well, in another work that was done by Pellegrino, Professor Pellegrino and Professor Modena, well, they execute an extensive program, but I will focus on only one very important aspect, that is the influence of the existing steel stirrups. Well, for instance, in this beam, where it was applied 3 layers of CFRP, it was installed in lateral faces. But in this case, we are also using, we are not using any type, or the beams does not have stirrups. So the existing shear reinforcement ratio is 0. So this beam has no stirrups. And when we apply the 3 layers of the 3 CFRP layers, we obtain an increase of the shear strength capacity for the beam. The increase was 51%. For the same beam, but with the difference of having a certain percentage of 0.33% in terms of existing shear reinforcement ratio, so assured by steel stirrups, we realized that we have the increase provided by the same shear strengthening arrangement was only 32. So this is also this is observed in all experimental research that is being carried out by several people, and so the shear strengthening effectiveness decreases with the increase of the reinforcement ratio assured by steel stirrups. Well, now how to evaluate, how to estimate the contribution of the FRP systems for the shear strengthening of reinforced concrete beams. Well, we will assume this approach that the shear resistance of reinforced concrete beams is the additive contribution provided by the concrete, VC, plus by the steel stirrups, and with the contribution of the FRP. Well, I have here the equations that are proposed by the FIB, the Fédération International Federation for Concrete, and the ACI, so American Concrete Institute, okay, the CNR, the Italian design guideline, and CDAR, it is the Australian design guideline. Well, in general, all of them are based on the requirement to estimate, or the necessity to estimate, what is the effective tensile strain in the FRP, or in the tensile stress in the FRP. But this is the tensile depends obviously on the effective tensile strain. Well, In this figure, I have the symbols used in the formulation. So that is inclination of the FRP, that is the inclination of the shear crack. dF is the distance from the top level of the FRP to the longitudinal reinforcement. The DFT is the distance from the top level of the FRP to the top surface of the cross section, okay? The DFB is the distance from the bottom level of the CFRP to the bottom level of the cross section, or the bottom surface of the cross section. And I think is RC is the ratio of the rounding, because in order to avoid stress concentration in the corners of the cross section, we must round these corners, and this is the corresponding radius, okay? Well, I'm presenting here the formulation of FIB ACI. So in case of the FIB, so this is the equation that we are using to evaluate the contribution of the FRP. And well, that depends on the shear strengthening ratio that is obtained from this equation in the case of using strips of CFRP from continuous, this is the equation. And now we need to estimate what is the effective or the design value of the effective strain in the FRP. And finally, it is used, we are using, or the FIB is recommending a safety factor of 1.2, 1.3, 1.35, depends on quality control assured when applying these shear strengthening systems in real practice. Well, we need to distinguish two situations. One situation is when we are using a full wrapping configuration, so where we are involving all the cross section. So in this case, FIB is proposing this equation that depends on the average compressive strength of the concrete, depends on the stiffness of the FRP system. While when we use a whole or side strengthening configurations, so the effective value, the effective strain, is the minimum of the value provided by these two equations. So we need to evaluate these two equations, and then the minimum one is the one that we use to evaluate the effective strain. So after we evaluate the effective strain, we replace this here, and we divide by the safety factor, and finally we have the design value to estimate the contribution of the FRP system for the shear strength according to the FIB. In case of the American Concrete Institute, so this is the equation that is proposed to evaluate the contribution of the FRP system. So it is recommended for the phi factor a value of 0.85, and for CF factor it is recommended 0.95 if we adopt a full wrapping configuration, or 0.85 in case of U or side configuration. And well, to estimate the effective stress in the FRP, we need to evaluate the effective strain, because the effective stress is the product of the elastic models of the FRP by the effective strain. For the full wrapping configuration, the ACI is recommending a value not exceeding 4 per mile. So we multiply the ultimate strain that is provided by the supplier, but ACI also recommends to affect the value provided by the supplier, take into account the environmental conditions. So in the document of ACI it is proposed, so this a factor take into account these environmental conditions, and then that depends, that the values varies between 0.5 and 0.95. So depends if we are using, for instance, also depends also on the type of materials, since carbon is not so susceptible to the effects of environmental conditions. So this parameter is higher in the case of using carbon fibers. So we multiply the ultimate strain of the material that we are using by 0.75, and this needs to be lower than 4 per mile. In case of using a hull oxide strength configuration, the ACI is recommending to evaluate the kappa-V factor, and this kappa-V factor depends on 3 types of parameters. K1, that depends on the quality of the concrete, is obtained from this equation. K2 depends on the type of strengthening configuration. For hull configuration, it is recommended this equation, while for side configuration, it is recommended this one. And finally, it is proposed this equation to evaluate the effective bond length of the FRP reinforcement that depends on the stiffness of the FRP system. In the case of in the case of FCNR, so it's a little bit more complicated, the formulation, but well, I try to summarize. So for the full wrapping and for the hull jack configuration, so this is the equation that is proposed to obtain the contribution of the FRP. And the critical parameter is the design value of the effective tensile stress in the FRP. So when we are using the hull configuration or full wrapping configuration, the CNR is proposing this equation. Okay, this is the equation that is proposed to evaluate the design value of the effective stress in the FRP. That depends on this design value of the effective stress that is evaluated according to this equation. Okay, so this is the equation that is proposed to evaluate this stress concept, and multiplied by the remaining part of the equation, we obtain the design value of the effective stress. So the FFDD is dependent on the elastic models of FRP, on the thickness of the FRP, but it is also dependent on the bonded joint specific fracture energy, GFK. And GFK is obtained according to this equation that depends on the properties of the concrete, okay, properties of the concrete substrata, and on the KB factor. And this KB factor depends on the geometry of the FRP system that we are using. So depends on the width of the strip and the spacing between the strips. So after evaluating the GFK, that is the bonded joint specific fracture energy, and after evaluating so we can substitute it here in this equation, and adopting for the gamma FT a value that is 1.2, we can obtain the FTD, And finally, if we evaluated the bond length, okay, that is obtained from the characteristics of the FRP as well as from the average tensile strength in concrete, so then we have all the information to replace in this equation and finally obtain the design value of the effective strain. And consequently, we are capable to obtain the contribution of FRP. Well, if we are using, if we are adopting a eject configuration, we need to, we have a different equation to evaluate the design value of the effective strain. In this case, we are using this equation. But the FDD is also obtained according to the equation already proposed, okay? For the side bonding configuration, the equation proposed to estimate the contribution of this shear strengthening arrangement is different from the previous one. So the equation is this one, where the design value of the effective stress is obtained from this equation, okay, where FDD was obtained from the equation that was already proposed for the O or U configuration. And finally, we need also to estimate what is the equivalent bond length that depends on the FRP slip at the bonding. So the symbol is SUF, and the value assumed for the FRP slip at the bonding is 0.2 millimeter. Okay, so this is the formulation of the CNR. In case of CIDAR, the Australian Design Guideline, the equation to obtain the contribution of FRP is the one here proposed, where we have the geometric parameters, that the geometric parameters depends on. So I represent these geometric parameters here, okay? So all this, the information that is represented in this figure, so is used now to evaluate these geometric parameters, okay? So this is the geometric parameters HFE, ZB, and ZT. And to evaluate the design value of the effective tensile stress, the CIDAR proposed two parameters. The one, that is DF, is a stress distribution factor, that is evaluated by different equations according to the type of shear strengthening configurations that we will adopt. And finally, is maximum design value of the tensile stress installed in the FRP. So if we use a full wrapping configuration, so we have here the equation that we should use to obtain the stress distribution factor, and the two equations that we have, or that is proposed to evaluate the maximum value of the tensile stress installed in the FRP. That depends on phi r per meter, whose value is 0.8. It depends on safety factor, whose value is 1.25. And if the ultimate tensile strain in the FRP is less or equal to 15 per mile, or 1.5%, so we use this equation to evaluate the FFT max. If it is higher, in this case, the the value or the FFT max is obtained multiplying the FR, or the FR is divided by gamma F, safety factor, and then is multiplied, this EF is multiplied by the ultimate strain, which means that is equivalent to the tensile failure of the FRP. Okay, this is the tensile failure of the FRP. In the case of if we adopt or if we are using a FRP system that has an ultimate strain higher than 15 per bar. So we are limiting in order to mobilize a certain aggregate interlock effect. For the case of U or side, for the U and side configurations, so we have different equations to evaluate it. The stress distribution factor, so the stress distribution factor is evaluated according to these two equations, depends on the normalized maximum bond length perimeter, lambda, and this lambda is obtained, this lambda is the ratio between the maximum bond length and the effective bond length. The maximum bond length is obtained from equations that depends on the type of configuration. So for U configuration, we are using this equation, while for the side configuration, we use this equation. And finally, the effective bond length depends on the characteristics, on the stiffness of the FRP, and also on the strength, on the concrete strength capacity of our beam. Finally, to obtain the maximum value of the tensile stress applied in FRP, so we use these equations, and we should evaluate the values of these two equations, and we will adopt the minimum value. Okay, so in this case, in this last equation, depends on the BL, that is a bond length coefficient, and on the BW, that is the strip width coefficient. But that depends on the characteristics on the FRP system and on the inclination, battery's inclination, as you know. So now the idea is to apply these formulations to a case study. Give me 1 second, please, to take some water. So imagine that we have a reinforced concrete beam with this geometry, okay, that has a width of 200. The total depth is 630. So this is the longitudinal reinforcement in the bottom, in the top, and it has also some steel stirrups. And well, the idea is to estimate what is the value or the shear capacity of the beam when we install strips of the CFRP with the width of 100, the width is 100 millimeters, indicated here. The thickness of the FRP is 0.167 millimeter. The ultimate tensile stress is 3000 megapascal. The Young's model is 300 gigapascal. The inclination of the FRP is 45 degrees, and we are using a wet layup. We assume that the concrete of this beam has a characteristic compressive strength of 16 megapascal, an average tensile strength of about 1.9 megapascal. The design value of the compressive strength is 10.7 megapascal. In case of steel, so the yield stress is 400 megapascal. The design value of the yield stress is 340 megapascal. The diameter of the steel stirrups is 6 millimeter, and the distance between the steel stirrups is 200 millimeter. And this is the properties or the geometric properties of the cross section. So the total depth is 670 millimeter. the distance of the total depth of the FRP, that is from the bottom surface of the flange to the axis. So the concept is DF is 417 millimeter. The BW, this is a mistake. The BW is 200 instead of 300. The D is the distance from top up to the longitudinal reinforcement, 630. And the radius of when we run the corner in order to avoid stress concentration, the RC is 25 millimeter. And we assume that this beams pertains to the interior of a residential building. And we are using a CFRP system. So now we will use the FIB approach to estimate the contribution of the FRP plus the Eurocode approach that was the edition of 1991. So nowadays we have a more recent one that we will use with CNR, because CNR is also a more recent approach. So the idea is to be coherent. So when FIB was published, this formulation to evaluate the contribution of the FRP, the document available to estimate the contribution of concrete and steel syrups was AC2 of 1991. And now we will start evaluating the shear strengthening ratio. So this is evaluated from this equation that depends on the thickness, on the width of the strips of CFRP, and on the width of the cross section and the distance between the strips. And then we obtain the corresponding value. To evaluate the effective strain, tensile strain in the FRP, well, it is the minimum between the two the values obtained from these two equations. So this is the first equation that depends on the average compressive strength of the concrete, that is 24. And now this is the Young's model, it is here, and the reinforcement ratio that we have just evaluated. And finally, we obtain a value that is 4.6 per mile. For the other equation, we obtain, so it's quite similar, but it is based on, or you should also consider the ultimate strain, that is the ultimate strain of the FRP, and we obtain about 4.9. So this means that the effective strain should be considered 4.62 per mile. So then I need to obtain the characteristic value, and the characteristic value of the effective strain is 80% of the effective strain, and then we obtain 3.7 per mile. And finally, in order to obtain the design value of the effective strain, we divided the characteristic value by the gamma factor, that for this case is 1.35. And finally, we obtain the value of about 2.7 per mile. And consequently, if we replace this value in the equation that is provided by the FIB, we finally obtain a value of 110 kilonewtons. Well, according to the EC2, the contribution or the shear capacity of the beam is the minimum between the contribution of the concrete plus the contribution of the stirrups, BWD. But since we have now the contribution of the FRP, we need also to add the contribution of the FRP. And it is the minimum between the contribution of these three terms and a term that takes into account or avoids the occurrence of crushing of the compressive struts that is formed. Okay, so we start evaluating the contribution of the concrete, okay? And according to EC2, we obtain a value that is about 45 kilonewtons. Well, for the steel stirrups, taking into account the distance between, or spacing between stirrups, that is 200, and considering that we are using stirrups of 6 millimeter diameter, and with a design value of the yield stress of 348, well, we obtain finally a value that is about 62 kilonewtons. And the term that takes into account or evaluates the maximum value that a beam can support in order to avoid crushing of the concrete. So that is obtained according to this equation. Well, finally, we obtain this value, 375, about 375, and consequently, we are able to estimate what is the load carrying capacity or the shear capacity of the beam. That is the addition of the contribution of the concrete plus the contribution of the steel, and finally the contribution of the FRP. And since the addition is lower than the term corresponds to concrete crushing, so this is the final value of the shear capacity of this beam, according to the Phi plus EC2. Well, now, if we apply the ACI, so in this case, we will use the ACI 440 design guideline to estimate the contribution of the FRP system, and the 318, the ACI 318 design guideline to estimate the contribution of the stirrups and the concrete. Well, for the FRP, so as I indicate to you, so we need to use the incremental perimeter that take into account that it is a residential. So this pertains to a residential building, and since we are using carbon fiber, so the ACI 440 recommends a value of 0.95. So we need to multiply this perimeter by the ultimate strain, and finally we obtain the ultimate stress that should be used in the formulation. We will do the same to estimate the maximum value of the maximum ultimate strain that should be used. So this is the 10 per mile is the ultimate strain according to the supplier, and then we multiply by the CE factor, the environmental perimeter, and then we obtain the maximum ultimate strain that we should use. Since we are using a U strength configuration, we need to evaluate the kappa V factor. This kappa V factor, then we will multiply it by the ultimate strain in order to evaluate the effective tensile strain. So, in this case, we need to evaluate the kappa 1, the kappa 2, and LEA perimeters. The LEA perimeters is obtained according to this equation that depends on the stiffness of the FRP. As larger is the stiffness of the FRP, as lower is the bond length, and consequently, lower the effective strain will be also smaller. So we need also to estimate the kappa 1 that depends on the characteristics or on the properties of the concrete, and since the characteristic value of the concrete is 16 megapascal, we will obtain a value of 171. So depending on the type of shear strengthening arrangement that we are using, in this case is U, so we should use this equation to obtain the kappa 2. That depends on the DF. DF is the distance from the longitudinal reinforcement up to the top level of the FRP system, that in our case is 430 millimeter, and then we obtain the value of 0.9. So replace here, we obtain from kappa V a value of 0.25. This means that the maximum or the effective strain should be 25% of the ultimate strain, and then we obtain a value that is about 2.3 per mile, that is lower than the maximum limit imposed by ACI, that is 4 per mile, and then we should use this 2.3 per mile. And we are now able to evaluate the effective stress, that is the product of de Young's model by effective stress, and then replace in the equation that provides the contribution of the FRP system. So now we can use the 318. One moment, please. We can use the 318 to evaluate the contribution of the concrete and the contribution of the steel. According to the ACI, this is equation to evaluate the contribution of the concrete, and this is the equation to estimate the contribution of the steel. And finally, we obtain the shear capacity of the strength beam, that is the product of phi per meter, that according to the ACI is 0.85, multiplied by the contribution of the concrete, 84, the contribution of the steel stirrups, that is 71, and the contribution of the FRP, that should be multiplied by this CF factor, that for hook configuration is 0.85. And finally, we obtain the shear capacity according to the approach. For the CNR, in CNR, we need to start evaluating what is the horizontal spacing between the FRP systems. Since the inclination is 45, so this we obtain 141 millimeters for the spacing between the strips of FRP. We need to, we should remember that the main equation is this one, and then we need to estimate the FFDD. The FFDD is obtained, this is the design value of effective stress, is obtained according to this equation that depends on the GFK, and the GFK is evaluated from this equation, okay? So that depends on this kappa V per meter, that we start evaluating the kappa V per meters that are depending on the geometry of the strengthening configuration that we are using. So this is the width of the strip, and this is the spacing between the strips, and then we obtain a kappa V factor that is 1.02, but since it should be lower than 1, we are adopting the value of 1. And this is the characteristic value of the compressive strength and the average value of the compressive strength. And then we obtain for the GFK the value that is 0.17 megapascal. For the bond perimeter, so we have all the information to obtain the value, and we obtain 140 millimeter. So then we have everything to obtain the FFFT, and considering for the safety factor a value of 1.2. Okay, so taking the previous information and replacing in the equation that CNR is proposing to obtain the design value of the effective strain, we obtain a value that is around 490 megapascal. And then if we replace in the equation proposed to estimate the shear capacity of a beam, we finally obtain a value that is around 109 kilonewtons for the shear, for the contribution of the shear strength beam arrangement applied in the beam. Well, if we now use the most recent Eurocode to estimate the contribution of the concrete and steel, and adopting for the inclination of the compressive strut, if we adopt an inclination of 22 degrees, and neglecting, as recommended by the Eurocode for this case, neglecting the contribution of the concrete, so we estimate the contribution of the steel, that is, and then we obtain the value of 138 kilonewtons, and where we are adopting for the inclination of the strut, as I told, the value of 22 kilonewtons. So, according to the Eurocode, the interval is between the cotangent of that is between 1 and 2.5. Well, finally, we need to verify if we need to assure that concrete crashing does not occur, and then we need to estimate what is the maximum value of the shear load that we can apply to the beam, and it, according to the EC2 from the most recent one. So this is the equation that we are using to estimate this value. So it depends on the new one perimeter, that is this one. Okay, this is the perimeter. Okay, this equation 0.6 multiplied 1 minus the characteristic value of the compressive strength divided by 250, and so we have everything to obtain this value. And since the contribution of the stirrups plus the contribution of the FRP is higher than the VRD max, so the term that estimates or avoids the concrete crushing, so we should limit the contribution of the beam to the value indicated obtained from the VRD max. Finally, using the CDAR, we need to estimate the final equation. So this is the final equation, if you remember. This is the final equation. And where we need to estimate what is the design value of the effective stress. The design value of the effective stress is the product of this stress distribution factor, DDF, multiplied by the maximum value of the design effective stress, the maximum value of the design tensile stress in the FRP. To evaluate the DF, we need to estimate what is the lambda perimeter, and to evaluate the lambda perimeter is the ratio between the L max and the LE, the effective bond length. So the L max from, okay, this is how to evaluate the L max, while the LE, the bond length, is depending on the axial stiffness and on the characteristic value of the compressive strength of the concrete. And then from these two values, we are able to obtain the lambda perimeter. And since the lambda perimeter is higher than 1, so this means that the BL and should be equal to 1, and the alpha 1 should be 0.31, while the DF, the distribution, or the factor that take into account distribution of the stresses along the depth of the cross section is estimated according to this equation. Then we obtain a value of 0.92. For the DF, we obtain a value of 0.92. So this means that here we replace DF by 0.92. We evaluate the maximum value, the maximum value of the design effective stress. This is the minimum value between these two equations. So this is provided by the minimum value. So in this case, this is the FIAR parameter. This is the tensile strength, and this is the safety factor. And to evaluate the second equation, so we need to evaluate it before the BL, but we know that is 1. The BW is evaluated according to this equation that takes into account the geometry properties of the CFRP. These values in this equation, and well, the minimum one, look, the first one we obtain 1,920, and in the second one we obtain a value that is around 588 megapascal. So this means that the value that we should adopt is 590, about 590 megapascal, and then this value is finally replaced here in this equation, and then we obtain what is the design value of the effective stress installed in the FRP. So now we use this term here, we replace, and consequently we obtain the contribution of the FRP. Comparing, according to the CDAR, and considering the Australian design guideline to evaluate the contribution of the steel stirrups and the concrete, so this is equation to evaluate the contribution of the concrete, while this is the equation to estimate the contribution of steel stirrups. And finally, we obtain the contribution or the load carrying or shear capacity of the beam, that is the contribution of the concrete, contribution of the steel stirrups, and contribution of the CFRP system. And we can compare in this table. I'm comparing. So in fact, the I-test value was obtained applying the CNR, the design, the Italian design guideline with the Eurocode, while the minimum value was predicted or was obtained using the CDAR and the Australian guideline. But the differences are not quite high for this example. Well, for the NES technique, the near surface mounted technique, so this technique, as I don't know if we have some knowledge on this topic, but well, what we use is we apply the FRP systems in the lateral surfaces of the beam. So we need to open or executing slits in the lateral face, in the concrete surface, in the concrete cover of the lateral surface of the beams. So this is, in this case, we see several slits open on the lateral face, so we need to clean. So then we cut the laminates or FRP bars. We are cleaning the FRP, in this case, the CFRP systems, and in this case we are using CFRP laminates. Then we fill the groups with the epoxy. We apply a thin layer of the epoxy in the lateral face of this laminates, and then we insert the laminates, and finally we remove the epoxy, the exceeding epoxy, and we finalize the process of applying the strengthening technique using the NSM. Well, to show you what is the potentialities of this technique for the shear strengthening of reinforced concrete beams, I will present fundamental results obtained recently in an extensive experimental program. So we carry out three series tests with three series of beams: series A, series B and C. No, sorry, four series: series A, B, and C, and finally series D. For the series A, B, and C, the distance of the monitoring branch or span of the beam, because in the LR span, in all the beams everything was equal. This means that the percentage of the steel stirrups are maintained equal, and the difference are resumed to this LI span, where we applied different shear strengthening configurations. In case of series A, B, and C, the LI span was 900 millimeter, while in the D span, the LI was 1,200 millimeter. Well, in all the beams, we introduce a very high flexural reinforcement in order to force the occurrence of a shear failure. And then look what happened in terms of the influence of the compressive strength of the compressive strength of concrete. In the beam C, in the series of beam C, we used a concrete of a very small compressive strength. So the average value was around 90 megapascal. In series B, we adopted a concrete of about 40 megapascal. And finally, in the series D, we used a concrete of about 60 megapascal. And in this graph, we have a relationship between the contribution of the FRP system that was composed by laminates. In this case, we use laminates, FRP laminates of cross-section 1.4 millimeter by 10 millimeter. So we use rectangular cross-section laminates with a cross-section area of 1.4 millimeter by 10 millimeters. And it is quite clear that when we increase the compressive strength of the concrete, the contribution or the effectiveness of the CFRP laminates increase significantly. For instance, using a concrete in the beams with a concrete compressive strength, average concrete compressive strength of about 40 megapascal was 1.5 times higher than the contribution of the CFRP in the series with the average compressive strength about 90 megapascal. For the series of beams with the high test average compressive strength, that was about 60 megapascal, the effectiveness was about 2.7 times higher. Another very important conclusion that we obtained from this series of tests is about the effect of the percentage of existing steel stirrups. At yellow color, we have the contribution of the CFRP beams when using the lightest percentage of shear stirrups, of steel stirrups, okay? Between 0.16 and 0.17. In blue, the percentage was 0.10. And from these graphs, it is clear that as higher, yellow is higher, as higher is, in general, as higher is the percentage of the existing steel stirrups, as lower is the effectiveness of the shear strengthening arrangements. Well, this is some types of failure modes that we observed. When we applied a relatively small percentage of NSM laminates, we realized that we have the bonds, but it is quite clear that this bonds has also is followed by the formation like a semi-cone. So we have the formation here of a semi-concrete cone. So it's a fracture of a semi-cone that is formed at the extremities of the laminate. So this means that, well, maybe we can have three types of failure modes. So we can have the rupture of the laminate, and we observe this when we reinforce the beams with the highest compressive strength. So in this case, in some cases, the laminates have even failure of rupture. But in the other case, we have the bonds, and that is followed by the fracture of the concrete surrounding the laminates. However, when we use a relatively high content of laminates, we observed this type of failure mode that is formed by the detachment of the concrete cover. So this is like, so it is like a wall that is in fact the concrete cover layer where the laminates are installed, and this happens mainly when we have a relatively high content of CFRP laminates. This is justified. We can justify this by a model that we developed in the last years. Because what happened? So as I told you, in the NSM technique, we observed mainly four types of failure mode. So the bonding for the NSM elements, rupture of the NSM elements, the concrete fracture, okay, and concrete fracture followed by a bond, a sliding. And since this, in general, this concrete fracture occurred, what happened? If we now analyze this small portion of the beam, where we idealize the shear, the critical diagonal crack, like a plane. So this is the critical diagonal crack. And when the crack width is increasing, okay, the crack width of the critical diagonal crack is increasing, well, we are imposing each laminate a loaded hand slip, and this loaded hand slip is transferred to the laminates along the bond length. So a force, and consequently we have the formation of this concrete, we have the potential formation of this concrete fracture. If the laminates are if they are too close, we can have interaction. We see this in the following slides. So this means, this is a cut. So I'm cutting this plane. I'm looking this plane. So look, this is the plane. This is the laminates. Look, this is laminate 1, laminate 2, laminate 3. And this is the projection of the cone in the critical diagonal crack, okay, in the critical plane. And if the laminates are close, what happens? We start having interaction of these concrete fracture cones. And this means that we start having a tendency of the detachment. Why? Because this tensile component, look, this is a tensile component. So we have a component parallel, and we have a component vertical to the web faces of the beam. And this orthogonal component is promoting this type of detachment. The detachment, look in this beam, the detachment that we observed. Well, since the contribution of the NSM laminates also depends on the concrete fracture resistance, this means that if we install the laminate deeper in the slit, so this means that we have a larger concrete surface. And if we have a larger concrete surface, we will have consequently a larger contribution of the CFRP for the shear reinforcement. And then we executed some preliminary tests to verify this. So what we did, we executed direct pull-out test. Okay, so this is the specimen. This is the bond zone. And we analyzed three configurations for the installation of the laminate. In this case, the laminate is installed at the surface of the groove. In this case, at 6 millimeter depth in the groove. And finally, at 12 millimeter. And look for the results that we obtain. Clearly, we have a clear indication that when we install the grooves deeper, where we install the laminate deeper in the groove, the maximum pull-out force increase. Look, the blue corresponds to the results when we install the laminated surface of the groove, and the green corresponds to the situation where we install the laminates deeper in the slit. So this means that, well, in fact, it is a good idea to install the laminates deeper in the groove. Of course, we are limited by the concrete cover thickness, but well, in general, we have a concrete cover thickness that is 20, 25, or even 30 millimeter. So this gives us the suggestion to execute an experimental program in order to verify the effectiveness that we can obtain by installing laminates deeper in the grooves. So we executed, we performed an experimental program composed of beams of almost real scale. Well, this is again the span of the beam where we changed the strengthening configuration, so everything is equal, apart the strengthening configurations adopted for this span, left span, the smaller in order to force the high test shear force in this zone. So we used CFRP, carbon fiber polymer laminates, with the ultimate strength about 3000. So laminates of 1.4 by 10 cross section, but we also use laminates of 1.4 by 20. And, well, in this case, for these laminates, the tensile strength is a little bit lower, so it's 2577 megapascal. So this is the Young's model, is 169 and 166 gigapascal, and this is the ultimate strain. And we use epoxy adhesive with a tensile strength about 20 megapascal, and the Young's model of 7 gigapascal. And look what happened. In the case of this first beam, well, in all the beams, we always use 3 stirrups, okay? We have the stirrup 1, stirrup 2, stirrup 3. We use the same in all the beams. And in this first beam, we installed 4 inclined laminates. Laminates are installed at 45 degrees, 4 inclined laminates, but are installed superficially. So we install at the surface, okay? So it's like this situation. So we install at the surface, okay? In the beam, in the second beam, the blue line, we install the same laminates, but deeper, okay, in the groove. But in order to avoid to have some injuries in the longitudinal reinforcement, so the grooves were only open from the top or from above the longitudinal reinforcement, okay? This is why the laminates that are indicated a blue color is from the top label of the longitudinal reinforcement up to the bottom surface of the flange. So the difference here is that we are installing the same laminates but deeper in the grooves. In this beam, what we are doing, the green one, we are installing 4 laminates. These laminates, in case of the beam red color and the beam at blue color, we are using laminates of 1.4 by 20. The cross section is 1.4 by 20 millimeter. While in the other 2 beams, we are using 1.4 by 10, cross section 1.4 by 10. Why? Because in this case, in these 2 beams, in the beam at green and the beam at gray, we are using not 4 laminate but 8 laminates. Why? Because in this case, for the green beams, we are installing 4 inclined laminates deeper in the groove, okay, from here to here, while, and we are installing also 4 other laminates at the surface, so from the bottom surface of the web up to the bottom surface of the cross section, okay, so, but all of them, all the 8 laminates are inclined, so the shear reinforcement is the same. And finally, for the last beam, what we are doing, we are installing vertical laminates deeper in the groove, okay, and inclined laminates at the surface, and consequently, these inclined laminates, they are installed from the bottom surface of the flange up to the bottom surface of the cross section. So in this case, so repeating, we install in each lateral surface 1, 2, 3, 4 laminates, vertical laminates deeper in the grooves, okay, from the top, from just above the longitudinal reinforcement up to the bottom surface of the flange, and the inclined laminates we are installing in all the length of the lateral surface, but we are installing with an inclination of 45 degrees. And I only highlight the relevant aspects. Look, for instance, if I'm comparing these two beams, this is the force deflection for all the beams, and if I'm comparing the shear strength contribution, for the beam where we install is the red beam, where we install 4 laminates but deeper in the surface, 4 laminates in surface, we obtain a shear strength effectiveness of about 68%, while when I install the same laminates but deeper in the groove, I obtain a shear strength effectiveness of 81%. So, in fact, we can conclude that if we have the possibility to install the laminates deeper in the cross section or in cross section of the beam, if in fact we have a higher effectiveness for the FRP systems. Well, since it's about 2 hours of lesson, I will only present the formulation for the NSM, and then it will be not possible to continue with that, where I had the idea to talk about the BTS, shear strengthening technique, and also the Dabazon, but it's not possible because, well, I have another compromise at 3 o'clock. So this is the equation or the formulation that is proposed by Professor Nani and his co-authors to estimate the contribution of the NSM system. So the contribution of the
Joaquim? 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 Hello. So I don't know why we are not hearing. Joaquim, maybe something's wrong. So we'll try with Joaquim to reconnect to see if he can finish the presentation. Joaquim is here, but again, you don't have audio. Joaquim?
Yes.
Okay, fine.
Yes.
We can hear you again. Your microphone is on.
So okay. So I'm going directly to. I'm almost finishing.
Okay, perfect.
Okay, so
It was 56.
I was presenting the NSM formulation. Okay, a moment, please. Okay, so I was explaining the Nani et al. Formulation. So the formulation proposed by Professor Nani and their co-workers. So I explain how to evaluate the L tot mean parameter, okay, according to this graphic representation. And well, we have also the equations that can estimate the number of the laminate that is crossing the critical diagonal crack. That is this number. And we have the equations to obtain the bond length for each parameters, for each I laminate. So this is the equation from, and using this equation we can obtain the L1, L2, L3, so the bond length for each laminate, and consequently we are able to estimate the contribution of the NSEM laminates for the shear strengthening of the beams. And well, based on and applying this model to beams that we tested, well, in fact, we obtain a ratio between the experimental and analytical that is, well, around 1.6 and 1.7. It is, well, it's acceptable. Take into account that is where we are handling with a quite brittle failure modes. From the extensive data that we collected, we realized that effective strains decrease with, or varies or decrease, in fact, decrease with the stiffness of the FRP, the percentage of existing steel stirrups, and also decreases when we are adopting a concrete strain class or a lower strength concrete strain class. And this is the type of evolution in terms of the effective strain with this parameter. And we realized that this evolution depends on the inclination of the laminates. So we have a higher decrease when we have vertical laminates and a smaller decrease when we use laminates at 45 degrees. And based on this data, we proposed an equation that depends precisely on these parameters, on the characteristics of the FRP, the characteristics of the shear reinforcement, the stirrups, on the average concrete compressive strength, and on the inclination theta. F is the inclination of the laminates. And using a safety factor of 1.3, we obtain, so we proposed an equation that in fact estimates with a very reasonable way or a good accuracy the values registered experimentally. So this is a relationship between the analytical values predicted by this equation, and the experimental ones. So we realize that almost all the information are in, or the values obtained experimentally are in safe side. And so this means that assuming a certain shear strength configuration and knowing what are the percentage of the shear reinforcement in the beams, and also knowing what is average compressive strength, and assuming a certain inclination for the laminates that we want to install in our beams, we evaluate what is effective strain, and we multiply the effective strain by the elastic models of the FRP, and then we replaced here in this equation to obtain the contribution of the of the FRP systems for the shear strength of the beams. Well, I have also another design guidelines, but I don't have time to present. So this PDF file will be available. So I think it's better to have this last minutes for some discussion. Otherwise, we will have no time for nothing, okay, for this type of discussion. Okay? Emmanuel, for me, I think is enough. It's more than 2 hours.
It was very, very good and very interesting, and a lot of details and important work you've done in the field. Well, we'll try to get 1 or 2 questions, and thanks again for this webinar. If there are any questions, just you can ask it in this public area. And well, if there's nothing coming, I will just maybe to open the discussion. This is an important issue, the last slide you present, because, for example, in the French guideline for shear strengthening, actually we limit the strain to a very low value, 0.2%. Whatever is the FRP strengthening, it means the young modulus or the steel ratio and so on. So I think that this approach is quite conservative, and it seems that your slide shows that we could try to make this value higher. Do you know if in any other guideline, ACI, CSA, there is some small evolution in this field to consider higher value of strain in FRP if the young modulus, if we use, for example, glass fibers or other fibers?
Well, in fact, the available experimental research clearly indicates that the effective strain depends mainly on the compressive strength of the concrete, on the inclination, on the shear, on the reinforcement ratio of the shear reinforcement ratio, and also shear strengthening ratio. This is clear, and depends significantly also on the type of shear configuration we adopted. For instance, if we adopt a full wrapping configuration, so it is the ultimate strain is much higher than the ultimate strain that we can estimate for the HU configuration and for the site configuration. So this is clear. This is obvious from the experimental evidence, and this is why it is fundamental to estimate to have equations that estimate or introduce, take into account this type of information. This is why we have this equation that clearly, in my point of view, represents the most important aspects that limits the ultimate strain. So limiting the strain to per mile is obviously too conservative in my point of view.
Okay. There is a question from Esmani. Where can we access the description of the concept that you present in the first part of your presentation? This question is right on the public area. Maybe I don't remember what was the first part, but maybe.
Okay. The first part, I don't know if, I can present the first slide. Can you tell me how I can go directly to the first slide?
Well,
how I can go directly? Because it's important to go to second slide where we have the index of the
yeah, I think we are nearby. It's by here.
I don't know. Please go. Okay. Okay. So almost. Okay. So please, can you allow Abou Fazi I don't know if it is correct, I'm pronouncing it correctly, but can you tell me what are the topic that you want? Is the fundamental concept of shear? Is the strengthening techniques? So please be more precise. Number one, fundamental concepts of shear. Okay, so fundamental concepts of shear is available in a lot of books because it's the fundamental knowledge or is the basic knowledge about shear. But if you can send to me an email and I can recommend you some books or many books where this type of information are clearly described. Okay, so if your main interest in this is getting information in the fundamental concepts of shear, I can recommend you one or two books where this information are detailed. Okay.
Okay, thank you, Joaquim. So, well, if there's no other question, what I propose is, if, of course, maybe send an email to get the details.
Okay, so I will send to you because it's indicating, I mean, concept of shear of FRP strengthening. Okay, so I can also send to you a document where we described the concept or the phenomenologies that is subjacent to the FRP shear strengthening. Okay.
I think it's perfect. Thanks a lot, Joaquim. Maybe he can send you an email and get the information directly. So I think we're going to conclude this webinar. Thanks to all of you to be here. Next one will be during March. We'll have 2 webinars in March, and the date will be announced on the website and by email. Feel free to send me an email if you want to be aware about all those these activities. Well, Joaquim, thanks again to be here. I will shut down the session, and then it will be available in maybe 1 or 2 hours in replay. So the link will be available for free if you want to send this very nice presentation and talk to friends or colleagues. Thanks again, Joaquim.
Thank you, Emmanuel. Thank you. Thank you, everybody. And it was a pleasure. Okay.
Thank you very much.